I have talked with literally hundreds of SAT students, and one thing I see with literally all of them is that Desmos is the fastest and easiest way to improve the most amount of points on the SAT. You've probably heard stories about people who get 800 on the SAT math section just because they understand Desmos really well. And while I can't guarantee you'll get that, I am pretty confident that any student who really takes time to learn Desmos well can get at least above a 700 in the math section on the SAT. I believe this because I've seen many students do it before. I've worked with students who literally were terrible at math before taking the SAT, but they just learned Desmos and they still got a pretty good math score on the SAT as a result of it. So in this video, I'm going to be covering everything you need to know about how to use Desmos for the SAT, plus also how the math works behind it, so you'll be able to solve these hardest problems that you see in Module 2. Now, I did already make a Desmos video in the past, but this one is going to go far more in depth. I'm going to cover everything you need to know about Desmos in this video. So if you're currently struggling, this video will literally save you. Now here's the thing, I'm sure most Desmos guides you've seen would just go immediately into the Desmos at this point. They would just open Desmos and start showing you different functions and different things you can write, different techniques immediately. But this is not the way you should be learning Desmos on the SAT. Because if you just learn a bunch of different Desmos tricks or Desmos hacks, you're not going to be able to actually solve these harder Module 2 problems. Because they're going to give you something that's going to be a little bit different from what you've seen before. And you actually need to know how the math works to be able to figure out how to approach these problems. So that's what I'm going to start this video by doing. Some of this stuff may be a little bit basic for you, but trust me, actually understanding this stuff will make everything so much easier. In fact, Desmos will become probably the easiest thing in the world after you understand how the math behind it works. So let's just start really basic. This here is a function. And the best way to think about this is putting an input to get an output. So let's say you own a business. And let's say that with one employee, just like the founder of the business, you are making, I don't know, $1,000 per month. Yeah, just 1,000. So I can say here 1 for 1,000. But let's say you now hire another employee and this person adds a lot of value to the business. So now you're making, you have 2 employees now and you're making, let's say $1,200. So that person added $200 worth of value. But let's say you add another person now and this person also adds some really good value. And so now you have 3 employees and you're making $1,400. So you started out with just 1,000 and now you're making 1,200 and now you're making 1,400. This is what is known as a function. You have inputs and you get outputs for each input. But we also have these things called equations that can be used to showcase what is happening in this function. So for example, this function here could be modeled by the equation 200x plus 800. Now, if you're wondering how I came up with this number, if you plug 1 in for x here, you will get 200 plus 800, which is 1,000. If you plug 2 in for x, you get 400 plus 800, which is 1,200. If you plug 3 in for x, you get 600 plus 800, which is 1,400. This equation literally just models what is being shown here in the function. But keep in mind, this is what is known as a linear equation. These equations always take the form of y equals mx plus b. And they're known as linear because they literally increase by a stable amount each time. You can see here that for every new employee, they only add $200. So plus 200 plus 200, if we add 4 here, it'd probably get to 1,600. So it's very linear, it's very simple. But you can also have here stuff with exponents. When you have an exponent in the function, it can be a little bit more weird. It can be something like, maybe let's say for one employee, you have $1,000. Let's say maybe for 2 employees, now you have $2,200. And let's say the third employee really helps, and now you have like $5,000. So as you can see here, this is not a stable amount. It improved by like 1,200 the first time, and now it's here by like 2,800. So it's really like big changes for each one. And so to show that, you need an exponent here. Now it would not be this exact equation because this is a quadratic, which would be a little bit different. But you can just learn here that this is another type of function known as a quadratic function. The way this works is ax squared plus bx plus c. And notice what I just did here. I just used letters to showcase how this works. And also for mx plus b up here, I did the same thing. When you have a letter that is not x or y, it is known as a constant. So a, b, and c would all be constants here, and m and b would be as well. They're called constants because quite literally, they remain constant the whole time. The 200 up here and the 800 up here, which would also be constants, never will change. It would always be 200 and 800. Whereas the x and the y will change. Like the x will always be changing. The x can be 1, 2, 3, and then the y will also always be changing. It can be any of these different numbers. So x and y are considered variables. They quite literally are variable numbers. They can be changing constantly. So this is a quadratic, and then down here we have an exponential. This is just yet again another function. This is definitely the least common out of the three that you'll see on the SAT, but it is something that can sometimes come up. And the way this just works is you have this number here, which has an exponent on it, which is x, and then you have a here, which is another stable number. So now let me just show you how Desmos actually works. Let me cover some of the basics real quick. So in order to get to Desmos, you just have to type this exact thing into the internet, and I'll put a link to it in the description below. This is the official College Board version of Desmos. There are not really many changes between this one and the typical version of Desmos, but it's probably just a good idea to use the College Board version because maybe it'll just get you more in the zone or something. As you can see here, you have a big graph that can include any point you possibly imagine. But you can also just go ahead and just type stuff here. So if you type 34 plus 34, you get 68 as the number. So like you can just like literally type any kind of calculation you want and you'll get the answer. It can be multiplied, it can be divide, make it into a fraction like that. If you type a decimal in like 0.34, you can click this thing on the left to make it into a fraction. So now you get 17 over 50 would be the fraction for 0.34. But what's really amazing is that you can also use functions in Desmos. So what this can be like is, say you're trying to find the mean of a set of data points. You can type mean 1, 2, 6, 7. And then you get literally the mean just there. So you don't have to do any of this kind of statistics work, any kind of statistics calculations. So that really saves a lot of time on the SAT, I gotta say. There's also some ones like median, standard deviation, minimum, if you're trying to find the minimum value, maximum, even stuff like the greatest common denominator if you want to find out that for some reason. And what's also really cool is you can type percentages straight into Desmos. So if you, for example, want to find 67% of 67, you can literally just type that into Desmos. And so you don't have to do any of the work of like moving the decimal places and all that stuff. It'll just give you the answer. So this is just incredibly powerful. You can also type trigonometry. So if I want to put the sine of something, so sine of 54 or 56. And speaking of which, if you click here on the wrench, you can change from radians to degrees. So that'd definitely be pretty important when you're doing these kinds of sine, cosine, tangent equations. If you want to make an exponent, you can just type Shift 6 on your keyboard, and that gives you an exponent that you can type in now. If you want to type a fraction, you just type the divide button, and that gives you a fraction. If you're trying to do something for an entire quantity, so like 45 plus 67, you can just highlight it and then do whatever you want to do. So I can just type fraction, for example, and then say 56. And finally, let me just mention constants real quick. So we have here x and y. These are both considered variables, like I explained before. If you want a constant instead though, like a or b or c, all you have to do is just type in that constant and then equals whatever you want it to be equal to. And the great thing is when you type this in, you'll actually get a slider here, which you can use to slide to make it whatever value you want. And if you want more places, you can also type in just a bigger number for here for the bottom thing. So now I have negative 100, and I can just really make it as big as I possibly want. So I can make it 1,000, for example. So if I have here y is equal to 3a plus x or something like that, I can literally just go ahead and shift it based off of where I put the a value. So it's really, really powerful. And if I want to change the step, so the amount it increases for each shift, I can also do that. So if I just want to move by whole numbers, I can just type 1 there. So now it only moves by whole numbers. Or I can make it just any number I want. So if I say like 6, 7, I now only can move a by 6, 7 points for each one. So just to finish my quota of random Desmos facts you might need to know, here's how to do stuff with intercepts. So as you can see, you can literally put functions in Desmos, which we'll get to in a second, but for these functions, they have x-intercepts and y-intercepts. An x-intercept is basically just where it intersects the x-axis. This will become important later on, trust me. But also a y-intercept is where they intercept the y-axis. The y-axis is the vertical one, the x-axis is the horizontal one. You'll also see for functions like this, you have something called a vertex. This is the bottom point, or it can also be, if you have it like this, the top point of a function that looks like this with the parabola shape. Thankfully, Desmos makes all this really simple because they have points you can click on, so you don't need to use any thought or use your brain at all for this, which should be very appealing for you. Bruh. So onto what I wanted to actually explain right here, single variable equations. So these are very, very easy to solve with Desmos, and you know it's a single variable equation because it only has one variable. X plus 3 equals 5. So you can see here that x is equal to 2 because it only passes through 2 as the intersection. Now that's just something you can memorize if you want, but if you want to think why this is the case, think about it like this. You have an equation here where x plus 3 is equal to 5. And so if x is equal to 2, then yeah, it works. 2 plus 3 is equal to 5. But if x was equal to like 7, then no, like 7 plus 3 does not equal 5, that equals 10. So therefore, x can literally only go through 2. If it goes through a number like greater than 2 or less than 2 or just any other number in existence, it is going to end up being wrong for this equation. Now I want to mention you can run into some situations with single variable equations where it just may not show up. So an example is an equation like this. You're putting it in there, but the x is just not showing up anywhere on the graph. There's actually a reason for this. The reason why is because these are literally the exact same thing. So literally every single value of x would work for this. There's not a single value of x that would not. So like if x is equal to 1, this would be equal to each other. If x is equal to 2, this would be equal to each other. So the only way that Desmos could show this is if they covered like literally every single spot on this entire graph with lines, which would just be kind of weird and a little bit bad. So an easy way to fix this if you counter this situation is just use y instead. So put each of the sides of the equation in and just make it equal to y. So 2x plus 4 is equal to y, and then the other side will also be 2x plus 4 is equal to y. So now you can see this, and we'll get to in a second how to use this to figure out the answer. Now on to systems of equations. So when you have two different variables, so both x and also y, it will create a line like this. It'll be a slanted line. And when you have multiple slanted lines, the place where they touch each other creates a solution. So if they only intersect one place, you have only one solution for the thing. But if they have no intersections, then you have 0 solutions. But if they're literally the exact same line, then you have infinite solutions. So let me show these examples now. We got 2x plus y is equal to 7, which we have here, and then x minus y is equal to 1. You can see here that they both intersect at this place. So when x is equal to 2.67 and y is equal to 1.67, they intersect. So that's where the solution is. For this other one here, you have y equals x squared minus 4, and then also y equals 2x plus 1. For this one, you actually have two different intersections. So there are two solutions for here, because each of these is its own solution. Now we can have some other stuff here as well. So if I have here like y is equal to 2x plus 4, you can see these lines literally never intersect a single place. So therefore they have no solution. Or if you have here y equals 2x plus 1, these are literally the same line. So all across here, if I just hide this for a second, it is only one line. If I hide the purple and now it's just the green line, they're literally on the exact same place. Now the great thing is systems of inequalities work very similarly. You just replace the equal sign with a greater than or less than sign, or greater than equal to or less than equal to. So like if you think back to these equations before, you were basically saying here y is equal to 2x plus 1. But you could also theoretically say y is greater than 2x plus 1. And so this should intuitively make sense here. You're not saying that it is equal to one line. You're saying is literally everything greater than this one line as part of the solution. And you might notice the line itself is actually broken here. The line itself is actually not part of the solution because it is only greater than. So that line itself would be equal to. So in order to make it the line as well, we would have to say greater than or equal to 2x plus 1. So now you can see the line becomes solid, so therefore the line itself is part of the solution. For a system of inequalities, you're just trying to find the place where they both have this double shaded region. Everything here is a solution. So there's not just like one solution for these, there's literally infinite solutions, but it's only the solutions in the region here. So let's try here. It asks, is 2, 5 in the solution set for the inequalities below? So we have these intersections now, and if I type in 2, 5, now it makes a point for there as well. We can see that 2, 5 is in the double shaded region, so it would be in the solution set. Now, same thing for this one here. Y is greater than or equal to x squared minus 4. Y is less than or equal to 2x plus 6. We can see here yet again, 2, 5 is in this double shaded region. I know this double shaded region looks a little bit weird because it's like a sliver rather than a whole thing, but it just works the exact same way. Onto functions real quick. The way these work is when you have something like y is equal to 3x plus 5, you can just replace the y for f of x. It literally means the exact same thing. Don't get confused if you see this on the SAT. The only reason you'd want to put f of x instead of y is because you can do some other stuff with it, as I'm going to show you in a second. So for example, like this, essentially y is equal to 3x plus 5 here. But we could also now put f of 5. So this will literally just show me what this equation would be equal to if x is equal to 5, and that would be 20. And I can also just make it, literally whatever number I want. What's even cooler though is I can also do this thing called transforming the function. So I could put here x plus 4. And so now I literally get a new line that is showing a slightly off version of the function from before. I could also say minus 4. Now you don't necessarily need to memorize how these transformations work, since you can just put it in on Desmos on the SAT and check it for yourself. But if you are curious, it is kind of like the opposite of what you'd expect. Like it goes to the right when you type negative, and then also the left when you type positive. You can also do here f of x with the thing outside of the parentheses, so plus 4 like that. And so I know this looks the exact same, but what it's actually doing now is shifting it upward, and then I now can shift it downward as well. So I know it looks like the exact same thing, but that's just because for this function, it's pretty similar. If I instead make this like, 3x to the 4th, okay, now you can see much clearer. The red one is 4 below the top one. Now, you've probably been told by somebody that regression is the hardest thing to learn with Desmos. Like I can tell you from my own experiences, I learned regression from 5 minutes of a SAT YouTube video. And after learning it that first time, I literally have never struggled with it before again. And I'm not like some kind of special super smart genius. Like it's just because it's not actually that complicated to understand it. You see, with regression, the core idea behind it is you're trying to, like before, find what different numbers are equal to, specifically different variables. But it's a little bit different for one reason. When you're finding regression, you typically have more than just 2 variables. So rather than just having these 2 equations, you'd have like a z in there. So, or yeah, it's like a z after the y here and after the x here. Now this is significant because you can only solve a system of equations if there are the same number of variables as there is equations. So as you can see here, if there's only x and y, you have 2 variables, but then also 2 equations here. So you can solve it with the way that I showed you before with those 2 lines. But now that you have 3 different variables, it actually is not possible to solve this with just the method that we were talking about before. You can kind of solve it, but it's not really going to work the exact same way, especially since you're going to have to treat z now as a constant rather than a variable. Because, as I said before, only x and y can be variables in Desmos. So how can we figure this out? The way is with regression without a table. Now, maybe you've heard about regression with a table, but there's also a way to do it without a table. So for example, I have in here in Desmos these 2 equations and also a slider because again, like I said before, z is counted as a constant, not a variable. So we have to do something a little bit different to make this into a regression format. When you're changing an equation into a regression equation, there are just 2 things you must do. The first is treat every single thing as a constant in the equation. So what this means is essentially for those x values and the y values, you have to actually, instead of just putting x and y, put x1 and also y1. The reason why you have to do this is because this transforms these into constant values. Now x1 is a constant and y1 is also a constant. Now it's not a variable anymore. And then the second thing with this is you have to, instead of putting an equal sign, put a tilde like that. This is what really transforms it into a regression. It literally has the word regression here. So you can tell like a big change just happened. And so you can do this with only 1 equation. But if you're given 2 different equations like you are here, the next step is then to align these equations together along with this other stuff I just explained. So how this will look is you'll take the left side of the first equation, so 2xz plus y, and then let me change that into regression form, so x1 and then y1. Then you'll also take the left side of the second equation, so that would just be x1 minus z. Then you go ahead and put in that tilde sign and then do the exact same thing for the right side. So the right side for this one is just 3, and then the one for the bottom is y1z. Okay, so now you have here these different parameters. So what the system is doing is essentially Desmos is trying to approximate what these 3 different values could theoretically be equal to make these equations work. So the thing is, you're not getting an exact measurement for this. You're just getting what theoretically could work to get these 2 equations equal to each other. Hopefully that makes sense. If it doesn't, rewatch the video until it does, because this is pretty important to understand. So you're getting this now, but now what if you want to like try out a different situation? Like what if you want to test out different kinds of parameters? So you could say, for example, put this sign in there first. Z has to be greater than 0. I guess I didn't really change anything because it already is greater than 0. But let's say what if it had to be greater than 1? They're testing if Z is equal to 2, this is what X and Y would have to be equal to. And you'll notice that is different than what it was saying before. Now, X and Y values changed when Z was greater than 0. So as you can tell, it's not giving you a precise number for each of these. It's just approximating what it probably is going to be equal to. And we could put any kind of parameter we even want in here. Like we could say, for example, X1 has to be equal to 5. So now it's literally just going to find what these different values have to be equal to if X1 had to be equal to 5. So you kind of have this kind of creativity with Desmos regression where you can literally just test out anything you possibly imagine and see what it gives you. Now, for this example here, we cannot solve it unless we were given some kind of extra information. We would have to know what the parameter has to be. Does Z have to be greater than 0? Does X have to be for all real numbers, etc.? And we'll see some examples like that below for how this can actually be in action. So let's look at here first. So for all real numbers X, this equation is satisfied and T and P are constants and T is greater than 0. So I imagine the average SAT student would look at this and be like, wow, I have absolutely no idea how I'm supposed to solve this. But now that you know Desmos regression, it actually is it's not even really hard at all, to be honest. So we just first start off by putting this equation into Desmos. Keep in mind, we only have one equation here, so we do not need to do that thing with the brackets from before. We can just literally put this exact equation in and then change it into regression form and solve it. Okay, so I have that in here now. And so we have these different numbers. Now we just have to look at what the constraints are. So what kind of things do we have to satisfy to make this true? So T and P are constants, and then T is greater than 0. So constant just means a stable number, so we already have that as being true. But then it says T has to be greater than 0, which is really the main thing we have to change. So if I go here to the end, I put the squiggly bracket and then say T has to be greater than 0. And now, as you can see, it changed it. But actually, yeah, I think it already was 1, so that doesn't really change too much. And now it says if this equation has infinitely many solutions, it's true for every value of X, what is the value of T? So that is the one other thing you often have to change, which is that X here, they're treating X as being equal to 1. But we want X to be any value you could possibly imagine. We want to basically treat X like a variable here. So to make that work, you have to literally put X1 equals, and then put a square bracket, 1 dot 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 10. What we're doing here might seem complicated. It's actually, again, pretty simple. We're just trying to test 1 through 10 for the X value and see what T and P would have to be considering that. So we have 10 different numbers to test from. So this kind of mimics the idea of testing, as they say, every value of X. I know it's only 10 values, but 10 isn't a lot of values for math. So now it's testing all the values for X. It's treating X like a variable. So we can say the value for T is 38, and that would be correct. So now that you understand the way to solve this, I would recommend pausing the video before each of these upcoming equations and just trying to think in your mind, or even pulling out Desmos yourself and trying to see if you can solve it. That's going to give you a lot better practice than just watching me. It's also a lot more interesting to actually test it out for yourself. So start doing that, but I'm going to solve the rest of these now. So we got this equation here, and then it says A is greater than 1, B is greater than 1. And you have B is equal to that, and then they say K is a constant, and what is the value of K? So we're gonna have to do the thing with the brackets again because we have two different equations here. So we put that and then say nth root, which gives you the fifth root, A third 5, and then B. Then tilde, you got B as 4/7 and A as 3K minus 1. All right, let's see here. So we have each of these, and it says that A has to be greater than 1, B has to be greater than 1. So let's put the constraints there. A is greater than 1, and then B is greater than 1. So we get these different things. So this is simple. K would just be equal to 0.683. So we don't have to say anything for K is 1 dot 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 10. The reason why is because it never says here that K is all real numbers. In fact, they say K is just literally a constant. So we don't have to worry about any of that all real number stuff. I know I'm using different things for each of these problems, but hopefully it makes sense of why I'm doing what I'm doing. It's just following the exact rules that I set up, originally for this regression stuff. So I have these two final problems here, but I actually solved both of these in a recent YouTube short. So I'm just going to put the links to those two YouTube Shorts videos in the description of this video, and you can just check out those if you want to see how to solve these, so you don't have to waste more time in this video itself. But it's really just the exact same thing. Nothing has changed about this. It's just the exact same regression process we were showing before. Regression with a table is definitely a lot simpler, I would say. And probably a lot of you may have heard of this one and maybe not the other one. So the simple idea behind this is that sometimes you're going to be given two different points on a graph, and you have to actually figure out what the line would have to be based off those 2 points. And the crazy thing is sometimes there are going to be different lines that work. So if you get given these 2 points on a graph, maybe they want you to find just a straight line that connects both of them. It's pretty simple. But they could theoretically ask you to find a line that goes like this, like something that kind of has this parabolic shape, or maybe it's like an exponential thing where it's gradually like getting higher and higher. So there's a bunch of different lines that could all work for this. You're just trying to find what they're asking you for. And that brings us to this thing called a table. Tables are very simple in Desmos. You just type the word table to generate them, and then you can put in whatever points you want. So if I have this, I can put 1, 5, 2, 10, 3, 15. So I get given these points here. And so let's say I'm trying to find a line for this. The easiest way to go about this is if you just click this kind of add regression button here, it will just literally find a line that works with them. So this is a linear one. I can also find a quadratic, if you remember before the quadratic thing, ax squared plus bx plus c. I can also find an exponential one here. So remember the a times b to the x power. So those are the 3 main ones you'll have to see in the SAT. I really don't think you'll see any of these other ones on the SAT. Honestly, I haven't really seen a question that involves any of those before. So these are really the main ones. So linear, quadratic, and exponential, just whatever the question asks for, honestly. So for this one, find the linear equation that corresponds to these points. So I would just go ahead and put those into Desmos now. Click linear regression, and then I see, yes, this linear line. The linear line would be y equals 2x minus 1.
Another one.
So we have that there, add regression, do quadratic, and that would be the equation here. Y is equal to negative 5 x squared plus 20x minus 10. So down here I have 2 other equations that you really should know for solving these Desmos regression with the table problems. The first one here is the vertex form equation. So this is actually just literally another way of writing the quadratic equation that I had up here. Essentially how this works is that you have h and k here, and hk is essentially the point where the vertex of the quadratic is. So any quadratic, if you haven't been able to tell by now, is going to be kind of having this parabola type shape where it goes like that, or maybe it goes like that and it has it at the top here. The vertex is this red point at the bottom here and at the top here, and so it would have the formula hk as for where it is located on the graph. So basically, when you write the vertex form equation, you can actually decide where the vertex of the quadratic will be, which you don't have the chance to do for a regular quadratic. Like there's nothing here to indicate the vertex for a regular quadratic equation. Now, the place where this might become useful, say you get this table here, and you put it into quadratic regression, you get this. But say the problem tells you that actually, nah man, they don't want this point to be the vertex, they want this point to be the vertex. They want the 315 to be the vertex of this quadratic. Well, you just kind of be cooked because they don't give you the option for a vertex form here. So you have to actually write the regression itself. And this is how you manually put a regression for a table. It's literally the exact same way as we were doing the regression without a table. It's the same format where we put y1 tilde, and then I put a x1 minus 3 squared, and then plus 15. Now keep in mind, this can be literally any formula you want, like any equation you want. I'm just using the vertex form because that's what we need for this problem. So as you can see here, now they put the vertex in the right place and we get the correct graph where a would be negative 2.25. Another thing that can occur is using the circle equation. Circle equation is another thing you do not get in Desmos itself. So the way this works is that hk this time is going to be the center of the circle, and then the r is going to be the radius of it, so how big essentially the side of it is. So if you see a problem that asks you to make a circle, you can use this instead for the regression. So just to provide an example of this circle stuff, because I know you might get confused and then beg for me in the comments. So you want to just write the exact equation. So it's not really that complicated, it's not anything different from what we've already been doing, but you do x1 minus h, and then we say squared, plus then y1 minus k, and then square that. Make it into regression format. Okay, we got that. And here's the thing. It is not going to show you the thing on the graph when you do this. The reason why is honestly too complicated to explain. So just know it's not going to show it for you when it's a circle. So you have to do another step, which is just writing it out. It's literally not hard. You can just type in, so negative 3 squared equal to x minus, we have h is equal to 1, so 1. then square that, then plus y minus 5, and then square that as well. Oh, and I guess I actually need to put this in parentheses there. Okay, so that gives me the circle there. So you just had to do an extra step, and now it shows up. So you just have to first write in regression format, and then write it not in regression format. This is only for circles, so as long as you remember that, you should be fine. Onto equivalent expressions real quick. This is actually pretty simple. It's actually a lot simpler than everything we've been going over so far. All you need to know is that when you get a problem like this where it asks you what expression is equivalent to this one, you can 100% solve this by hand. Like you can just like combine the like terms and find, using that what the answer would have to be. But if you want to solve this with Desmos, what you can actually do is just put this into Desmos. So I just put this first expression into Desmos, and since we only have y's here, I can just make it equal to x. Typically I'd say equal to y, but since there's y's, we can do that instead. And so that gives us this really kind of weird function here where it's like, it goes up there, it has this kind of like squiggly thing. It's kind of weird. But what we can then do is basically just put each of these different expressions in and find which one matches with this one above. So I could just take the time to put each one of these in, but I already know that's going to be a for the answer. So if I have this for a and then I have that equal to x, you can see here it matches the exact thing that we had before. So if I take this off, it's literally just the blue. I put this back on, it's clearly covering it. So that's just how it works. I had mentioned circles before, but let me just talk about them a little bit more. This is the equation for a circle. So you can just put this in and you'll see a circle generated there. But what if you want to find stuff like the radius of the circle or the midpoint of the circle? What you have to do is you have to make essentially a point for each of the different points of the circle on the far edges. So for here, I'd put a is equal to 3, 10. And then I can see down here we have b is just 3, 0. And so now that I have this, I can literally find whatever I want to find about the circle. So I could say the distance between A and B. And so now I know the diameter of the circle is 10. Also, if we want to find the center of the circle, we can literally put the midpoint and then A, B. And we'll see that it is 3, 5 there. Not really too much else you need to know about circles, but this is a fun thing that you can try doing. And finally, onto factoring. Most people don't actually know this Desmos hack, but it's actually extremely powerful when you see a problem like this. So if you want to determine if something is a factor of a bigger expression, all you have to do is literally just put the first thing into Desmos and then the second thing into Desmos. And what you're looking for now is to see, do they have the same x-intercept? When I say x-intercept, I mean, do they have the same place where they intercept the x-axis, obviously? And they do. They both intercept the x-axis at 5, 0. But if we change this around a bit, like if we put x minus 6, now they don't have the same x-intercepts. They intercept the x-axis at different places, 5, 0, and then also 6, 0. So if they intercept the same place, the smaller one is a factor of the bigger one. If they don't, then they don't. The final thing I just want to talk about is when to be actually using Desmos. You see, the biggest rule of thumb I can give you is that anytime when you see an expression, an equation, or a point in a SAT problem, you probably should be using Desmos to find the answer for these. But if you don't see one of those, chances are you can solve this problem by hand, or you just don't need to use Desmos in the first place. Now keep in mind, there are many different ways you can use Desmos to solve problems. You can use regression, you can do the single variable and systems of equation stuff we talked about up here. But another good rule of thumb, so I have this table here that shows you when you should be using Desmos for different things. Desmos algebra is that stuff I discussed at the beginning of this video, like systems of equations, systems of inequalities, single variable equations. You should be using that stuff whenever you see a SAT problem with a single variable equation or system of equations, system of inequalities. So that's pretty obvious. Regression without table, you should be using this whenever you have more unknowns than you have equations. So if you remember the rules that I explained down here, we had 3 different unknown things here, x, z, and y, but only 2 different equations. So we had to use regression without table to solve for it. Here we had x, t, p, and we only have 1 equation here. So we definitely had to be using Desmos regression without a table to solve it as well. Regression with a table is when you're given points and you define out something about the function that connects them. That's pretty obvious as well. So when you see points, I talked to some students who are like, they see a points in a problem, like they see 2, 3, and then maybe they see 5, 10, and they think to themselves like, man, I don't know how I can solve this problem. But I always tell them, regression with a table, like it's almost always going to be that. Like don't even think about it. It's probably just going to be regression with the table if you see points. Now, if you see something else like with a circle or factoring, statistics, trigonometry, percentages, ratios, unit conversion, that can all be solved with just other random Desmos things. So for example, if you remember the statistics stuff like the mean, median, mode, trigonometry, I also discussed the circles, the factoring, ratios and unit conversion, I literally just have those here because these are other different equations you could put into Desmos. So it's nothing new I have to discuss. It's just another type of equation you might see that you might have to use Desmos for. And also by hand is whenever you see something with algebraic operations, geometry, or interpreting word problems. When I say algebraic operations, I mean when you have an equation like this, like if you have 2x plus 3 equals 5, and you add like 2 to each side, for example. So if you had to do that for some reason, you can't really do that with Desmos. Like there's no way to really easily do that. You will have to do those by hand. But chances are you will not have to do that, so chances are you probably can be using Desmos. Geometry and interpreting word problems, that's also pretty obvious. The geometry, like, you know, these are different shapes you're working with word problems. There's these different concepts you have to actually figure out. So maybe Desmos can be used for like a calculation here and there, but they're not going to be the main thing for solving those problems. Hope this video helped you.
This at SAT, yeah, it's pretty mean. Trying to judge my whole life off of tests on the screen. One shot, one run, no pause to rewind. If I panic, I'm done. If I trust, I'll be fine. Yeah, this SAT got my chest on freeze every second on the clock, trying to cut through me. But